Welcome to Brain Vision.
Okay, so this question is also on heat current. Okay, so this question requires us to calculate how much heat per second that flows from a boiling water into an ice and water mixture through a long rod. Now, in this situation, this long rod is basically made up of two types of metal. One is made up of copper, and then the other made up of steel. All right, and it's asking us to calculate the heat per second that flows from the boiling water into the ice water mixture. So basically, what it's asking us is to calculate the heat current. So let's project a diagram for our question. All right. So this is the side with hot water, and this is the side with cold water. So we have hot water here, and then we have water with ice. So okay, so this is our long rod. Okay, with some part of it made up of copper, and then the other side made up of steel, which we don't know the length. So let's say L2. Now let me do that. L subscript S for steel. All right, and then the copper end is 1 meter long. The copper end is 1 meter long. So as usual, boiling water at 100 degrees Celsius, and then cold water at 0 degrees Celsius. Okay, now the area of this rod is giving us 4.0 centimeters squared. 4.0 centimeters squared. All right, so let's move on to look at how we can solve for the heat current. So we know that our heat current equation is given as K times area into bracket TH minus TC, divided by the length. But in this situation, we don't know the length. We don't know the length of the steel. However, let's see how best we can go about it. Now, what we need to know is that we can calculate the heat current for copper and then equate it to the heat current of steel, because at the junction where they are connected together, they will have a thermal equilibrium. They will all be at a thermal equilibrium. So we can say that the heat current from copper will be equal to the heat current of steel. All right, so picking the information for copper, we can straight away go on and calculate for the heat current of copper. Now, the thermal conductivity of copper is 385 watts per meter per Kelvin. Okay, and then that of steel is 50.2 watts per meter per Kelvin. All right, so let's move on. So considering the heat current for copper, we can say that H or Cu, let me do Cu, is equal to the area. So let's start with the thermal conductivity, 385 times the area, which is 0.004 meters. Don't forget the area is 4 centimeters, so converting to meters, this is what you get. To bracket 100 minus 65. 100 minus 65. That is the temperature between them, the thermal equilibrium temperature between them, or the steady temperature between the joints of the two rods. All right, so all of this divided by the length of the copper rod, which is 1 meter. Okay. All right. So at the end of the day, we have H subscript Cu is equal to 5.39 watts. So this is the heat current that is associated with both rods. The heat current associated with both rods at the junctions. All right. Now the B part says that we should calculate the length of this steel. So remember, we say the heat current of copper is equal to the heat current of steel. All right, so since we calculated the heat current of copper to be 5.39 watts, we can equate it to the heat current of steel, which is 50, the thermal conductivity, 50 times the area, 0.0004 into bracket, the temperature 65 minus 0. Remember, 65 is the steady temperature between the two rods minus 0, and the 0 is the other end of the still, which is inside the ice and water mixture. All right, so all of this divided by the length L2. So straight away we can make L2 the subject, and then we'll have L3 equal to, when we compute this, it will give us 1.305 divided by 5.39, and this should give us about 0.24 meters, which is also equal to 24 centimeters. All right, 24 centimeters.